Hello, another circular motion question. Diagram and text. Let's go through the text, add things in. Particle P, mass 5 kilograms. So we've got 5g going down from P here, adding our forces in. Might as well put the tension on while we're at it. That must be one string going up there. Don't know what's going on the other one. Attached to two light inextensible strings, AP and PB, or BP as they've put it. The other ends of the strings are attached to fixed points A and B. So we've got two tensions here, a T1 and a T2. Particle moves at constant speed of v meters per second in a horizontal circle, radius 0.6 meters. So let's put that on, 0.6 meters. Center B, the angle of 20 degrees they've given us. Both strings are taut. Find the tension in the string AP. Right, so that's T1 we're looking for there. Right, so it's moving, it's told us in a horizontal circle. So we know that P isn't moving up and down, so we can resolve vertically and use Newton's second law there. So we can say that T1 cos 20 degrees is going to be equal to 5g. So T1 5g divided by cos 20, which is, tapping it in the calculator, 52.1 newtons. So that was fine. That was a quick 3 marks. Speed of the particle is v. Yeah, they've already told us that. Show that the tension BP, so T2, as I've drawn in my picture, is given by this. Right, so this is our circular motion bit then. So if we're moving in a circle, we know what the acceleration is, which means we can use Newton's second law. Our centripetal force in this case is going to be the component of T1 plus T2 acting towards the center of the circle. So we've got T1 sine 20 degrees plus T2, which is what we're trying to work out. And that is going to be equal to mv squared over r. So 5 v squared divided by 0.6. So that's going to be multiplied by 5 over 3. Okay, well, we know what T1 is. That is 5g divided by cos 20. So we've got 5g tan 20 degrees. I'm going to change this T2 to what they've called it, TBP, just to make sure we're using the same labels for all of these things. And then 5v squared times 5 over 3. So that's 25v squared over 3, which is already looking pleasingly like what we've got here. So yeah, all I've got to do is take 5g tan 20 degrees off of both sides, and then we've shown that. So that was straightforward. But again, we're just using the old thing again of our acceleration is v squared over r, or it would have been omega squared r if we had been using angular velocity, but we're not in this case. Right, find v when the tensions in two strings are equal. Okay, that should be fairly straightforward. So T1 is, so we want 5g divided by the cosine of 20 degrees. That's our one of our tensions. And then the other one we just worked out here is 25 over 3 v squared minus 5g. I'm going to write this as sine 20 degrees over cos 20 degrees because then it gives us some opportunity for getting rid of some cosines out of all of this. Right, let's get everything on the flat because we don't like all of these all these fractions that we got floating around, and we can divide everything by 5 as well. So I'll get rid of that 5, that'll become a 5, and get rid of that. Then we can multiply everything by 3 cos 20 degrees. So we're going to have 3g is equal to v squared cos 20 degrees minus 3g sine 20 degrees. And now we just have to, oh, I've left that 5 out from there. Now we just have to rearrange this, make v the subject. Well, I'll start with v squared. So v squared is going to be 3g 1 plus sine 20 degrees divided by 5 cos of 20 degrees. And now we just have to square root that. So I'll just take that squared off of there, save me writing it all out again, and whack the square root on. Right, so I've got to type all this in, which is going to take a while. This is another one of these stupid exam questions where they insist on you giving things to 3 significant figures, which is mystifying when they don't do it all the way through the question. They don't even use a value of g, which is the 3 significant figures, so I don't know why they want an answer to that. So I'm going to stick, having finally typed all of that in, to 2.9 meters per second as v, rather than pushing my luck with going to 2.991 or whatever it is. I've hit clear on the calculator now, so I can't remember what the third figure was anyway. But yeah, same old thing. Just, I know I keep reiterating this over and over again, but this is just the same. We're just using Newton's laws again with this particular finding that we have for circular motion. So another fairly straightforward question.